Okay, hello everybody. Hello. Oh, someone's waving up the back. Hello, person up the back.
Shh. Please be quiet now.
That doesn't work? Shh. Okay, that works. If I go loudly enough, you will be quiet. Hello everybody, and welcome back to another fun-filled COMP1511 lecture, or so I hope. Today we are going to be looking more at malloc and looking at a cool new thing called lists. So the things that you should be able to do after the lecture, if you also learn and practice and all that stuff, have a better understanding of malloc, be better able to reason about dynamic memory management, so working with malloc, have a basic understanding of lists, self-referential and linked data structures. This will all make sense by the end. It's a bit echoey. Cool.
Shh. Be quiet.
If you want to talk to your friends, the place to do that is outside. I genuinely will not mind if you leave to talk to your friends. If you're going to be in this lecture theater, please be quiet so the people around you can hear and learn. Please, I will presumably continue saying this over and over again for the rest of the lecture because first years can't listen or can't learn, I suppose. Okay, so admin, assignment 2. How many of you started assignment 2 last night because I said go home and start it and you want to make me happy? At least 5 of you. Thank you. You make me very happy. There's been a new video added. The tutor who made a video explaining the rules has also made a video explaining the input. So how to actually parse and understand the input. So watch that video, it should be good. It's linked in the assignment spec. Like I said yesterday, assignment 1, marking in progress, tutors will give you feedback. The week 8 weekly test is due tonight. And don't forget about the help sessions. There are assignment 1s running as well, so there's more times than usual. So if you look on the course website, you can see that. Cool. So looking at a bit of a review of yesterday, but with the syntax actually on the slides this time, malloc is a way of allocating memory in the heap, or as I was sort of saying, the hand-wavy cloud. Importantly, the memory we allocate with malloc lives forever or until we free it. So unlike memory inside a function, like the memory inside a function, when that function ends, that memory is gone. But when we allocate memory with malloc, it will continue to live forever or until we free it. The syntax for it is malloc and then the number of bytes to allocate. And it returns a pointer to the block of allocated memory, so the address of the memory, so that we know how to find it. In terms of how many bytes to allocate, if we want 100 ints, how many bytes do we need to allocate? Is it 1,000? Is it more than 1,000? Who has no idea? Someone said 2,000. Why would it be 2,000? Can't see the person who's talking. It would be a multiple of 1,000? Yes. Specifically, it is some multiple of 1,000, where that multiple is the size of an int. So an int itself, in memory, takes up more than just 1 byte. If we allocated 1,000 bytes, we wouldn't be able to fit 1,000 ints. We'd be able to fit some fraction of those. But in terms of how big an int is, it turns out there's a C function. It's not really a function, it's a magical macro, but we'll call it a function for now, called sizeof, which will tell you how big a type is. So for example, size of int will give you the size of an int. It will probably be 4 bytes, but it might not be 4 bytes. If you're on a little tiny embedded processor, it might be 2 bytes. If you're on a 64-bit machine, it might be 8 bytes. It's probably 4 bytes. If you use the sizeof function, you don't have to guess. You will just know that it is actually 4 or 8 bytes. A few interesting things. Size of int star is the size of a pointer to an int. When you're looking at allocating memory for structs and struct pointers, this is very easy to get mixed up, the size of the struct pointer versus the size of the struct. So careful about the size of pointers. More on that later. So size of int 10 is going to be 40 if an int is 4 bytes. And so on. So the syntax that we normally use to allocate memory for 1,000 ints is 1,000, or malloc 1,000 times size of int. And this returns the address of the memory that it's allocated, so we can store that in an int star p. So p is a variable that holds the address of an int, so the int star means. And so here, malloc will give us that memory. It'll make a blob of memory for us. Then it'll say, here's where it is, and returns that address, so we know how to get to that memory. Cool. So it would be really nice if things never broke, ever. If everything always worked perfectly and nothing ever went wrong. What a world it would be like. That is not the world we live in, unfortunately. It's possible that malloc could fail. Why do you think malloc could fail? Like, what could happen when malloc can't give you memory? Any ideas? So not what would happen if it didn't, but what would cause it to not give you the memory?
Not enough memory.
Yeah, not enough memory. That's the only one that I can think of. If you're trying to allocate memory and you don't have that much memory left, you can't allocate that much memory. One of the students a couple of days ago had this really fantastic bug where they were allocating memory and then in the assignment code, and it would run and run, and then sometimes it would hit the point where their assignment crashed. And it worked fine in GCC, and it worked fine in DCC Valgrind, but not in DCC. And this was actually a bug in DCC. The one and only time I've seen a bug, like, my code doesn't work in DCC, it was actually DCC's fault. So it has happened once. But what was happening there, when they allocated memory, it kept allocating more and more memory until it tried to allocate a gigabyte of memory. CSE won't let you allocate a gigabyte of memory. So in terms of the syntax for this, when malloc can't allocate memory, it will return null. Have we talked about null yet? I don't think we have. So when we have a pointer, it points to a memory address. The way we indicate that it doesn't point to a memory address, so our pointer points to nothing, is to make it point to null. So we'd call that a null pointer. So in this case, if malloc can't allocate the memory, it will return null. It will return a null pointer saying, hey, I couldn't do this. And we can check if p is equal to null, then we know things have gone wrong. So in this case, I've got an fprintf to std error, which is the standard error. It shows up on the terminal, but it can be used redirected to files and so on, saying error couldn't allocate memory. And then exit 1. I'm not sure if I've talked about this. Exit will exit your program. And exit 1 is like saying return 1 from main. It's saying something went wrong. So exit 0 would be like returning 0 from main, saying things are all good. Normally, you would only use exit when things have gone wrong and you need to quit for some reason. Cool. And when we're done with the memory, we need to free it. So this syntax for free, or the function for free, it takes in a pointer to the memory, as in the pointer that malloc gave us to the memory. So the new line in there didn't work. Pretend those are on two different lines. So it will release the memory that malloc gave you. It has to be the memory that you got from malloc. Like, you can't just give it a pointer to somewhere random in memory. It has to be like, malloc gave me this memory, and here's the memory, please free it now. What do you think happens once the memory is freed? Like, what do you think happens if you try and use it once you've freed it? Any ideas? I will accept bad things as an answer, yeah? It's okay to use it? No. Once you have freed memory with malloc, so malloc has given you memory, you've said, okay, I don't want this anymore, please free this memory, and you use it again, things are very bad. It's officially like illegal C to use memory after you've freed it. It's one of the big classes of security vulnerabilities. So once the memory is freed, you are not allowed to use it anymore. And then there's, of course, Newton's third law of memory management, that for every malloc, there is an equal and opposite free. And we talked about this a bit yesterday. We need to free memory because there is a limited amount of memory. If we don't free our memory, we'll just use more and more over time. It's not, you might say, oh, but Andrew, my code runs and it quits after like 10 seconds. It's not going to cause problems. When your program ends, the memory is freed. But if your program is a bigger program that does more than 10 seconds worth of work, then you'll use up memory on the computer. Like Chrome, for example, or any program like Windows, you need to reboot it to fresh itself up and be good again. So here's some code to put it together. So we have an int star p, which, remember, means p is a variable of type int star. and int star meaning an address to an int. P equals malloc, some really big number times size of int. If P is null, if it didn't manage to allocate, printf error couldn't be allocated exit 1. And then in here, what? It's frozen. There we go. In here, we can use it to do whatever we want, use the memory for whatever we want to use it for. And then at the end, we can free it. And then after this, we can no longer use that memory. Cool. Is that all good? Are there any questions about that? Or are there any meta questions like, Andrew, please slow down, or Andrew, your microphone sounds weird? Yeah?
What does exit 1 mean?
Say that again, what does exit 1 mean?
Exit 1 mean?
Cool, so exit 1, when you call this function, the function is called exit, it will exit your program. So your program will keep running until it hits this exit, and then your program will quit. Yes, it'll terminate the program. Yes? Yes, so the question was, when you free up memory, isn't that so you can use it for something else? Yes.
Can you just say if you free memory, you can't use it again?
So I probably explained that badly, I'm sorry. When you have, malloc gives you memory, and then you can use that memory. It's given you, say, 1,000 bytes of memory. When you call free, you're saying, I no longer want this 1,000 bytes, and so it can be used by some other memory. When someone else calls malloc, now they can have this 1,000 bytes. Does that answer the question that you had? You're looking confused still. Person at the back? Cool, so the question is there a difference between the printf and fprintf? Printf prints to the terminal, normal printf. Fprintf prints to a file stream, I think it's called. So you can fprintf to standard out, just like a normal printf, or fprintf to standard like I had here, which will print to the standard error stream. So you can, that's semantically what you'd use to say this is an error. Cool. What's the point of printing to standard error if it just shows up normally in the terminal? Is that your question? What a good opportunity to talk about semantics versus syntax. So there's this concept that I'm not sure if we've talked about. I've talked about in the forum a lot. By the way, how many of you haven't been to the ed forum? You haven't logged in, you can't log in? Only like one of you. Okay, if you can't log into the forum, then you should post on the forum and I'll help you out. Hang on. If you can't log into the forum, you should email me and I'll help you out because it's really useful. There's lots of stuff there. I've literally written over 50,000 words in forum posts. I could publish a novel. With the forum post answers I've written, I should do that because they're fantastic answers. Right, but back to the tangent I was going to go on. In C program, we have a thing called syntax, which is the rules of the language. Valid C syntax is code that will work and do what it says it will do. We have another concept called semantics, which refers to the meaning behind the code. So, this is a good example. So when we print to standard error, it'll show up in the terminal just like a normal printf. But semantically, the meaning behind it is saying, this is an error. There's something going wrong in the code. This specific message that I've printed out here is related to a problem in the code. And so even though they show up in the same place if you run your program normally, it means something has gone wrong. And so you can redirect, for example, you can move all of this stuff from std to be in a log file that you read later on, if you have a big program that needs log files. Cool. Does that make sense? Okay, so let's do a little bit of malloc coding. Is this way. I will grab this big piece of code. VLab. And by the way, the code from yesterday, if you've downloaded it from the website, it was really messy because I'd added some stuff right at the end, talking to students, and not deleted it. So if you download it again, I've changed it, I've added comments, I've made it all actually make sense, actually be like it was in the lecture. Cool. int main void. Cool, here is my beautiful program. So what this program would do is nothing that we can see, but inside the program itself, it will allocate us a whole bunch of memory. That's 100 million or 100,000? 1 million. 3, 6, 7, 8. It's 100 million, I think. 100 million times the size of an int, so 100 million ints worth of array size. If it can't allocate that, it'll print out saying there's an error, we couldn't allocate the memory. Inside here, we will do nothing with it because we're boring people, and then we will free the memory and then exit the program. So this program will either do nothing or it'll print out an error message. If you forget to do the ampersand when you're running gedit, you can Control Z and then type BG for background. Cool, malloc.c. Cool, so I'm getting some compiler error messages. Don't we love it when this happens? I'll try zooming out a little bit. Cool, so one of the skills that you'll learn over your career as a person who writes code is how to understand error messages, like how to get the useful information out of the error messages. Because this is just like a big blah, all this text. You just need to learn to read the important parts and understand what you need to do about them. So looking at this error, implicitly declaring library function, blah, 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 blah. The ECC is telling us what we've done. Did you forget to hash include stdlib? Yes, we did. So we'll fix that. .h. Cool. And it's also saying the same thing for free. Did you forget to include the header file in which free is declared? So it hasn't told us that it's inside stdlib. Maybe they should fix that. But we know that it's inside stdlib because we added it. Cool, and now it compiles. So we ran our code and nothing happened. Cool, very exciting. Congratulations, you've written a program that does nothing, just like in week 1. But let's do something meaningful with this. So one of the things that I think was confusing yesterday, or confusing forever for many people learning pointers, is the difference between making an array and making a pointer and using malloc. So I would do my best to explain it now, and then if that fails, I'll draw some pictures. If we have an array like this, I have made an array, I've made 10 ints worth of space in the function's memory. If I do this, I'll call them array 1, array 2, I'm so original. 10 times size of int. If I do this, I say int star array 2 equals malloc 10 times size of int. I have told malloc, please give me 10 ints worth of space up in the heap, the magical cloud, which is not part of the function memory, and give me the address of that. Both of these have created 10 ints worth of memory. This one here has made the memory inside the function's memory. And so when the function returns, the memory is gone. And this one here has allocated memory in malloc, which the memory will stay there until we free it. And I'm going to write this down. Cool. And so we can use the array notation to index into both of these. We can say array 1 index 0 equals 10, and array 2 index 0 equals 10. The syntax is exactly the same, even though one of them is an array with the square brackets, and one of them is an int star with the malloc. Who is confused by this? Who is like, what? That's so weird. Nobody at all? Okay, a couple of people. An important concept to understand here is the concept of the pointer pointing to the memory and the memory itself are different things. So the memory with a square brackets array is memory inside the function. The memory with the malloc is memory somewhere over here. And we have the names array 1 and array 2, which are both pointers to different pieces of memory. So I could say int star array 3 equals array 1. what I've done here is I've said, make me an int star, a thing that will hold the address of an int, called array3, and make it be equal to array1, which is equal to the address of the memory that array1 contains in the function's memory. So then I could go array3 equals 10. And these two lines here do exactly the same thing. Sorry, array3, 0. Does that sort of make sense? Yes. Say that again, why do you have to use star? As in for this thing here? Cool. So the question is, why do we have to have int star here? Int star is a type of like an int pointer, which holds the address of an int, or the address of a block of ints, in the case of an array. So int star holds the address of an int, whereas an int by itself, it's an int, it holds a value. It holds some sort of number. So if we want to have a pointer to an int, something that stores the address of an int, we need an int star. If we want to just have an int itself, we have just an int. Does that make sense? Still confused? Sorry, someone's asking a question and I can't see where you are. Is it an array? I'm sorry, I can't hear you. Yes, isn't an array a reference? Yes, and that's the thing that I'm trying to explain somewhat badly. When we have array here, oh, you're saying isn't this int array, but it's not a pointer to an int? Maybe. So when we have int array1 square brackets, we're saying give me array1 a variable of type int array of size 10. So this is the same as having an int star, the same type. This will be a reference to or hold the address of the memory that it has in the function memory. An int star to array will have the address of whatever int it's pointing to, which could be the same thing. You might be less confused now.
I'm confused about the next line down at 21. Does that put the contents of array1 into array3? Or what does that do?
That's a very good question. Does this line put the contents of array1 into array3? No, it doesn't, and I think this is where I need a diagram to draw. And if you're thinking like, oh, Andrew, you're wasting time, this is actually going to really help with the thing we look at next. If you understand this now, the next bit will be super easy. More inputs, laptop, objective 2. So by the way, you'll notice that in the Echo 360 recordings, it's only ever the computer screen that's recorded. This is because thanks to the fantastic copyright protection things inside my tablet, I can't put it on the Echo 360 recording. If I tried to put this on that projector, it'd just go green and be like, you can't do this. You might be recording movies from your tablet. So I have to record them separately. And then when I've done lectures with the tablet, I'll put the diagrams on top and put them on YouTube because I can't edit the Echo 360 things. So in the lectures thing on WebCMS, links to lecture videos are diagrams. Cool. Where were we? So I've got int array 1, 10. And so what this means is I have 10 ints worth of memory over here. That is approximately 10. When I say int star array 3, and so let's say this block of memory here is at memory address 0x100. So this is the address in memory that it happens to be at. When I say int star array 3 equals, in the wrong color, equals array 1. When I have a thing of type int star, that's saying it's a pointer. It's effectively an arrow. You can think of it as an arrow. So this thing, array 3, is an arrow that points to this memory here. And so when I say int star array 3 equals array 1, I'm making the arrow point somewhere different. In this case, the arrow is pointing to this block of memory up here that I allocated for array 1.
So then if you change something in array 1, and then you call it with array 3, it'll be the same as what you changed in array 1.
Yes. So the question was then if I change something in array 3, will it also change in array 1? And yes, that's exactly right. If I say array 3 position 1 equals 20, because array 3 is a pointer, array 3 is an arrow that points somewhere else, rather than actually having the array memory itself. This means go to array 3, go to the array index 1, and make that be 20. And so now if I printed out array 1, index 1, it would also be 20. And to prove that to you, I will do it here. So I'm going to initialize my array to be all zeros. So array 1 is now just 10 zeros. Let's save this as. Get rid of the malloc. So I'll just print out array 1 index 0, right? And so this should print out 0. We expect that this will print out the value of array 1 and index 1 and index 0, which is the number 0. And then if I set it to be equal to 20, and we'll print it out again, it will now be 20. Hopefully this is all good because you've done arrays heaps now. And so for now, let's just do that. Oh my god, it compiled. I didn't forget a function prototype. I don't have any functions, which is probably why. Cool, and so we can see array 1 index 0 is 0, array 1 index 0 is 20. We have the array, we print it out, we change it directly, it's changed. And now for the actually interesting part. When I say int star array 3 equals array 1, this means that the variable array 3 is like an arrow. Is that how you spell arrow? Maybe. That's not how you spell array, array 1. So array 3 is this arrow here that I've drawn. I'll draw it in green. It's this thing here that points to where this memory for the array is. And so if I change something in array 3 index 0 is 100, and then I print out what's in array 1 index 0, that should now be 100, if I'm not lying to you. So this code starts out all zeros, I set the first one to 20, I make array 3 be a pointer to the memory from array 1. So when I change something in array 3, I'm actually changing it in array 1. I do that, and then I print out what's inside array 1. And if all goes to plan, I'm not lying to you. Cool. So we can see after we've changed it down here in array 3, we've changed the contents of array 1. Does that sort of make sense? This is a bit of a confusing concept, but the way that I think about it that makes sense for me is that when you have an int star, that's an arrow to something, and that's separate to the memory itself. So you can change where that arrow points, and that'll be referring to a different piece of memory. Cool. Hopefully that is all good. Is that all good? Yep. Does it matter which order you put it in, as in?
No, as like 26 below like 28.
26 below 28? Yeah. That is a very good question. Does it matter which order this is in? So does it matter if this line is above line 28? Let's try it and see. So I reckon this is not going to compile because it's going to go, what is array 3? You haven't told me about array 3. It's down there. But let's see. There we go. Use of undeclared, identify array 3. Did you mean array 1? Because they're close names. So at this point in time, array 3 doesn't exist. But what I could do is make array 3 exist up here and then set it to be equal to point to array 1 down here. And so doing it this way means, we don't care about that, DCC, go away. We don't care about the mistake that's about to happen. There we go, cool, something bad has happened, we've got all the red. So it's saying runtime error, store to misaligned address blah for type int, which requires 4-byte alignment. Man, this error message was the bane of my existence when I was trying to cheat on that thing that I cheated on the other day. DCC, why do you do these things? But what this is saying is, where did this strange number come from? What is this address? This is the value that happens to be in array 3 before we initialize it. You might remember from the various times we haven't initialized things. I'll print out what's there. %p, array 3. When we don't initialize a variable, it has whatever happens to be in memory from before, which is not usually what you want.
Is it safe to use uninitialized variables to seed random number generators?
Is it safe to use uninitialized variables to seed random number generators? No. It's illegal to use an uninitialized variable. The C police will come and arrest you. So we can see over here, we printed out the value of array 3, so what array 3 points to, which was this address here. And then it said, you're doing a bad thing. Don't do that bad thing. Did someone say something? But if I put this up here, so I make array 3 be initialized, make it have a value, in this case the address of array 1, it will not crash. Cool, and so indeed, it has done what we wanted. It's changed array 3, which has actually changed array 1. Cool. It's a very good question. Let me undo back to the original code. Cool, there we go. No, I saved it over arrays 1. How do I undo Shift Control Z? Erase 2. Cool. I'm just trying to keep the versions of the files so you can look back to the various ones later on. And anyway, life is hard. So, hopefully this is making some sort of sense. Sorry, the microphone keeps moving away. Hopefully this is making some sort of sense. One of the students posted a link on the forum last night to a video from Richard Buckland, who used to teach the previous version of this course, explaining pointers. I highly recommend his lecture videos because his lecture videos are fantastic. Like, he is the best lecturer ever. His lectures are fun. You go to them for fun, not because you want to learn things, and you learn things anyway. So I highly recommend checking out that lecture video, and it's another person explaining pointers, which might be that person who finally makes you understand it. Not that one, that one. Cool, so let's move on to something new. And let's stop recording and let's put that one over there. So, arrays, right? Arrays are great. You remember arrays. I've seen arrays. Lots and lots, and my diagrams are broken and I don't know why, and I tried really hard to make them not break, so I'm very sorry. I'm not sure what's going on there. Maybe I am. Anyway, so arrays are a contiguous block of memory. Contiguous means a whole bunch of things stuck together. Each item has a known location. We know where the next array element is because it's next to the previous one. If we do, int array 7 equals these numbers, we get this block of memory that's not actually off joint because the diagram is not broken. So we have these series of boxes all glued together, one after the other, that each stores one int. Right? Cool, this is good, this is familiar. But it's kind of bad if we don't know how big our array needs to be in advance, or if we need to increase the length of the array. So we have an array that's 7 big, right? But if we want to make it then be 20 big, we can't do that. You can't make an array bigger after you've made the array. And I mean, we can use malloc, but that's still effectively fixed in length. Like, once you've malloc memory, you can't go, actually make it bigger. Someone's going to raise their hand and say, yes, you can use realloc, but realloc is bad. Don't use realloc. But when we allocate memory, right, all the ways we've seen so far, we allocate memory, it's of a fixed size, that's it, you can't make it any bigger. So we need a new way to represent collections of things. So rather than having arrays where everything is glued together, we could have lots of individual things, right? We could allocate all of these, one single int for A, make it be, make the value be 3, allocate another single int with malloc, make another single int malloc. And so here we go, we have these, oh man, that is really, really unreadable. It doesn't get better if I zoom out. Does it get better in like Internet Explorer or something? I'm going to laugh really hard if this actually works better. Tutor at the front is screaming because I'm using Internet Explorer. Ah, it doesn't work at all. Very good. Firefox. Why did I push that button? Firefox. That's a little bit better though. Just kind of squint and use your imagination. So we have our array before, right? And it's all these numbers glued together. We could make individual things. So we could make a single element effectively, a single thing to hold this one thing and this one thing and this one thing. And that'd be great if we wanted to make more of them, right? We can just go, and make another one and make another one. And that's all good except that we have to somehow keep track of all of these pointers, right? Like, we've got the problem now, how do we keep track of them? We could make an array to hold the pointers. The same problem with like arrays not being able to be resized, right? So there's this really crazy idea here. If we want to store these individual blobs, but not have to keep track of where all of them are, we can make each of these know how to get to the next one. This is called list. It's sort of working. So before we had our array that was 3, 1, 4, 1, 5 all glued together, we could make all of these be individual allocations to hold just one element, but then have each allocation know how to get to the next one. And so 3 knows contain the value 3, and the one after me is over there. And 1 knows, I've got the value 1, and the one after me is over there. And so on in this beautiful, almost not entirely broken diagram. And so the way that we would describe this, we'd call one of these a node. And so we would have a sequence of nodes, each of which has a value and where the next one is stored. So the memory address of where the next one of these nodes is. Here's some example code we could use. We could make a struct. Struct node. Contains 2 things. It contains a struct node star next. So remember, struct node star means a thing that stores the address of a struct node. And it contains an int data, so the value inside it. And so by doing this, we can have our little blob, our little node, know both what its value is and how to get to the next one after it. And so we can make one of these nodes, give it the value A, make another one, give it the value 1, and then make, is it meant to be called next? Cool. Make A.next be equal to the address of B. So we're saying A.next, its field contains the memory address of B, aka how to get to B. So we can draw a diagram by showing, look, it's joined like this. And we can set B.next to be null. Like I said before, null pointer means it's not joined to anything. And so this means when we're using our code, we can know, if at the end. But this still has the problem of we need to know where A and B are and all of them to set the things right. Because we have a pointer in our struct, this one here, we can use this to get to the next node. And so the syntax for getting to a thing, if we have a pointer to a struct, we dereference the pointer with the star and then set its .next to be null. And so this is very ugly. It's like if we had star I if I is an int, set it to a value that had put the value into I. This one puts it into the value of a next. That's really gross to look at. We have this convenient syntax with arrows to save us having to do this ugly thing here. So what this means is if a.next is a pointer, a.next arrow stab if you're Jashank, arrow next equals the address of C. So this is like saying inside the struct node A, the next field of that contains a pointer to a struct. And if we dereference that next field and get to its next field variable, we give that the address of C. And so that's saying A next, which is this B, setting its next field, setting this arrow here to be the address of D, C, yes. And then we can go A next, 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 so A's next is B, next is C, next be the address of D, and so on. So that is the end of the slides, but that is not the end of the lecture. Because if I just gave you slides and you did slides and no coding, you would never learn anything. So here's something I prepared earlier. So this is just the struct from before. Shh. Are you talking because you're confused, or because you're bored, or because... I'll explain that in a bit once I've done some code. Is that okay? Someone said confused. Are you confused because this is confusing? Shall I get into some code and then if you're still confused, we can try and be less confused then? Cool, one person nodded. Int main void return 0. Cool, and so who remembers how to make a struct? How to like make a variable that is of type struct node? Was very confusing. If I want to make inside the memory of main a new struct node, how do I do that? Has anyone been paying attention to any of the lectures recently? Someone said struct, yes. Node, someone said node, yes. What do I need after this? A name, cool, we'll give it the name. An important thing to understand here, struct node is the type. So it's not that struct is the type and node is the name. Struct node itself combined like this is a type, like int or char or int array. And this is called name. It's a boring name, I'll call it A. It's an even worse name. So to reference into the fields of a struct, into these things that are the two elements inside the struct, we can go dot, so a dot data equals 10, a dot next equals, what do I make this be equal to say that it's not pointing to anything? Null, yes, because null means this is not pointing anywhere. If I didn't do this line, what would be inside the a dot next field? Shall we find out? A dot next. Print out the value. A dot data is and a dot next is cool. So we make a struct node A. So we've made a blob inside the memory of the function that contains these two things. We've set its data to be 10. We're printing out what's inside the data and the next fields. It compiled, it's amazing. And so we can see a.data is 10, and a.next is some strange memory address that's not what we want it to be. So if I put this one here and I actually make it be equal to null when I'm creating my node, a.data is 10, a.next is nil. That's the way it's telling me that it's null. Okay, who wants me to draw some pictures to explain this because you're confused? Quite a few people. Let's do that. Laptop, project 2. 3, 2, 1. Learn things. So when I have the code struct node microphone's hidden again. When I have the code struct node A, that means inside the memory for the main function in this case, make me a struct node, which is a box of shape, a pointer to the next node, and the value inside. So when I say a.data equals 10, I'm filling in this data section here with the number 10. And when I say a.next equals null, I'm filling in the next field with null, a null pointer. Cool. Does that make sense so far? Cool. And so then when I print out a.data, that means inside this variable a that's in our main function, in the memory of our function, go to this field down here, the data field of it. Cool. All good so far? So let's make a function to print out the nodes. We can do lots of them. Void print node. I'll leave that for now. Put that down there. I'll make it be called node because that's a better name. Oh. Node. Cool. So if I want to have my print node function print out the contents of a struct node called node, what do I need to put in here? If I wanted to print out the contents of my struct node, what do I need to give it? If I wanted to do something with a thing, I have to give it the thing. Yes? Functions are all good, hopefully. So struct node. So I've made myself a variable called node of type struct node. And then I can call print node on A. I'm not going to forget my function prototype. Cool. So what this will do, it'll make the node, put the things in there, call print node. Print node will take in that node and print out the data in the next. Hopefully. Be compiled. Cool, and so it does the same thing as before. Everything is good. But let's make some more nodes because it's boring to just have that one node. Struct node B. B.data equals 20. B.next equals null. Let me draw these conceptually as well. So when we're sort of drawing our list nodes here, it's got the value 10, and then it's got the pointer to the next thing in the list. So when I've just done this here with A, it points to null, it points to nowhere. Instead of writing it null like that, we just do an X because we're lazy and or bad at writing neatly. Cool, and so this is saying I have a node, contains the value, the data 10, and points to nothing. When I do this line here, struct node B, I'm making myself another node. Here, giving it the value of 20, making it point to null. So I have two nodes, they're two blobs of memory. They both point nowhere. They're both just blob, they don't have any link between each other. How do I make this one here A point to this one B? First of all, in terms of the picture that I've drawn, right, I want to make this arrow go over here. Do you agree that this looks like the right way to make it point to the next one? Make the arrow point to the next one? Cool, all good. And this is the next field in the struct, which contains a pointer to another struct. So this is this one here, a.next. So if I want this one to be pointing to B, what do I do? What's the syntax for that? Someone said something ampersand B. I'm liking the sound of that. Because ampersand B means the address of B, the location of B in memory. Let me put B in memory over here. I really wish you could do this on paper. It's so good. 20. Cool. And so I'll give this a memory address. 0x100, 0x200. These are not realistic numbers, but they're just numbers. So if I want A to point to B, if I want A's next thing to be, hey, the next thing after me is B, it's over here, I need to give it the memory address of B. And so to get the memory address of B, I use &B, which means get me whereabouts in memory B is. And so if I want A's next to be this, how do I do this? Just the same as up there. A.next equals B, equals the address of B. So this means now, in my little diagram here, the arrow from A points to B. And in terms of the actual value in memory, A's next field is now the address of B, so 0x200. So this same one here. Does that make sense so far? We have made a node, this struct blob that's got a value and the pointer to the next thing. We've made another one of those. We've made the first one point to the second one by making its next field have the address of where the second one is in memory, so how to find that second one. I think this is probably a good time to have a break. Are there any imminent urgent questions, like Andrew, you didn't say this thing that's really annoying and you should tell everybody now, or is everybody good? I said we should have a break, and so now everyone's going to stop paying attention. So let's have a break for 10 minutes. Feel free to come up and ask questions. And also don't just sit down the whole time. I say this every time, timer for 10 minutes, just a sec. Okay, those are the beeps of please be quiet now. Oh, that worked. Clearly I should beep instead of shushing at you. So, shh. Welcome back. I hope that you had a good break. Did anybody just sit down the whole time? You're bad people. Stand up now and then sit down again. No, you're just going to stay there forever. You're lost, man. Cool, so I had some good questions over the break, and the answer to those questions was, we're going to look at that next, so let's look at that next. One of the questions was like, if we have to keep making this node A, node B, and so on, we haven't really achieved the purpose of being able to make as many as we want, of like any length we want, right? And so the way that we would do this, let me chuck that back over there. Laptop, two. Is it recording? Yes, it is. So first of all, conceptually, the way that we would do this, and I'll draw pictures, and then after the pictures, yep, it's gonna fit. Cool. After the pictures, we'll look at code, but pictures first tends to help. So if we make ourselves a node, like we did before, so there's sort of the integer part and then the pointer to the next one part. And then we make another node. The thing keeps not thinking. Oh, sorry. Is that better or worse? Better, hopefully. So, shh. We have our node. We make a new node. We draw another square on our piece of paper. We give it a value. And then we make the previous node point to this new node. Like this. And so then to add another node onto our list to make it hold another thing, we make a new node. We put some value in there. And then we make the node before that point to this new node that we've made. And so the way that we can like make a list that's arbitrarily big is by making a node and then making another node and another node. So if we wanted to, for example, like scan in numbers until the user said stop scanning in numbers and then put all of those into a list, every time we read in a new number, we can just make a new node and join it onto the list. So whenever we want to make a new element for our list, we just make an element and then join the current end one to the new one that we're adding. So I can make another one, put another value in it, 2. Then I would join the previous one to that, and so on. So conceptually, does this make sense? The way to add more things onto a list, we would call this a list or a linked list because the things are linked together. The way to add new things onto it is to make a new thing and then make the end of the current thing point to the new thing. So if we made a new node up here, we make that one point to that, and so on. Do we need to always add it to the end? Could we add it somewhere else? Is there any reason we couldn't add it to the middle? Someone said no? Yes, correct. There is no reason we can't do that. So if we decided we wanted to add a node, this new node here, between 20 and 30, we can, I'll make it be 100, give it a value. We can just say 20 now points here, and 100 now points here. So in an array, if you wanted to add a value in the middle, good luck. Like, you can add an element into the middle of an array by, say I've got 5 elements and I want to put it in the second slot. I'd have to move the second one to the third slot and the third one, and like copy all of the array values along one and then put it in the freed up slot. You don't want to do that, right? But if you've got a list, you can just decide, oh, I'm going to put this between these two nodes. So make the node before it point to this new node, and then make that point to the new next node. Cool. Conceptually, does that make sense? Someone had a question, yes? Cool. So the question was, how does it work in the code? What a good question. Let's look at that now. Are there any other questions about the diagram conceptual before we move to some code? Cool. So let's do a diagram that matches the code. So I've got myself struct node A. Here is my struct node A. Has the value 10 and points to null. I then make myself a struct node B. Has a value 20. It points to null. When I say a.next equals address of B, I'm saying conceptually A now points to B. And in terms of the actual values of them, I'm saying A's next field now contains the address of B. So A now knows how to get to B. And then I've printed out the node, which just prints out the values of the node. If we then wanted to add something after B, let's add one called C. C can have 30 on it. Cool. And so how this works, I've now got a node 30 called C. Put that in here. And so I could say b.next equals the address of C, right? So I could say in this element B that, I know where B is, I've got the value of right here, I know how to access B. Make its next field point to C. But this defeats the purpose of having the linked list where we don't have to store all of them. And so the other way that we can do it is by going via A, which tells us where B is, and then going from there to C. And so the way that we would do this, let's save that as like list 0 or something, list 1. The way that we would do this is we would say, get me the next field from A. So that is, I'll grab a different color, this one here. This arrow here is like A next, that's the pointer. Remember I said pointers are effectively just arrows. So this pointer here is an arrow that points to the next thing, or it's a memory address of the next thing. And so when we say a.next, we refer to this element here. And then if we want to get its next field, that points to the element. Let's try and get this. That points to the element itself. If we want to get to the next field of that element, so this, this bit here that contains a pointer to the next one, we can dereference the pointer that we have to B. So go to this memory address, and then in that memory address, access its next field. And then the syntax for that, to dereference something, we take the star of it, like this. So in a less confusing example, if I had int I and then int star p has the address of I, to dereference p and get to I would say star p. So star p equals 10 means I now has the value 10. It goes to the thing that p points to, which is I, and changes the value inside that. And so we can do that. We can say go to the address that's stored in A next and dereference it and then set it to something, and that's really ugly syntax. Programmers like to be lazy, and that's so much to type. And so we have a shorthand of that, which is equivalent to a arrow next. No. Let me try that again. So this gets us to the struct itself, and then to get to its next field. And let me go back to my diagram. So when we say star A arrow next, we say this arrow here that points to B, this pointer, go to that node, and then go to its next field. So its next field is, highlighter, this one here. And so rather than having to go to this thing and then dereference it and then go to its next field, we can use the syntax of a.next arrow next. And so this also refers to this bit that I've squiggled in blue in the diagram. Who's thoroughly confused by this? Only a couple of people, that's a bit surprising. So I'll keep going on. For now, just keep in mind when I say something arrow next, I mean go to like the, let me try that again. A next arrow next means this. I'll say the words again when I've actually got the words right in my head. So let's continue looking at this example. We could say b.next is equal to c. A.next arrow next is the same as b.next, because when we dereference a.next, we get b. And so then if we go to b.next, that's like saying b.next. So then the equivalent syntax there is go to the thing a.next, which is the pointer to b, go to its next field, which is this one here, and then set that to be equal to the address of c. And so that is saying we go to a.next, which is this pointer here. We go to the field, go to the thing that it's pointing to, which is b. We go to its next field, which is this one. Can you see? You can see. Cool. This next field here, which is this one here. Man, the screen just went dark. And then you set its value to be the address of C, which is doing this bit here, making the contents of its pointer be the memory address of C, telling it how to get to C. And so then I can make another one called D, struct node C, struct node D, D, A.next arrow next. Next equals the address of D. And so this is saying go to A's next field, which is this one here. A's next is here. Go to the thing that it points to, which is B. Go to its next field, which is this bit down here. Go to the thing that that points to, which is C. Go to its next field, which is this bit down here, and make that point to D, which would look like this. Cool. Does that make sense to some extent, sort of? Sort of making sense? Which thing is that? Is this a pointer? Yes. So the A.next here refers to the next field of the struct, which is a pointer to a node. And then the A.next arrow next refers to the next field of the struct that A points to, which again is a pointer to a node, so it's a pointer. And then its next field is the next field of the next field of the thing that A points to. Cool. That may or may not have made sense. But you can see here I'm doing this A, B, C, D making struct on the stack. I haven't achieved the make as many things as I want to make. And so I'll save this as list 2. Let's, instead of making all of these nodes here like this, let's dynamically allocate some nodes. So let's create a node with malloc, which will do the same thing. It'll make us a node exactly the same, a blob of memory to fit these two things, the index and the data. But instead of it being inside the function memory, it'll be inside the magical malloc heap in the sky. And so how would I write that code? Rather than making a struct node A here, I want to be doing something is equal to malloc something. So what's going to go in these somethings? Someone pick one and tell me what should be there. Yes, some number times some size of something. Very good. So malloc, remember, gives us the number of bytes that we've asked for. So if we want to have one struct node, we don't have to have the 1 times. It's just making it really clear that it's one that we want to have. times the size of struct node. And so this will give us 1 times however many bytes big this is, dynamically allocated, so up in this memory over here. And what does malloc return? What does malloc return? Yeah, pointer, it returns the memory address of the memory it's made. And the type that holds a memory address is something with a star. Some type here, pointer. And so what's going to go in here? I'll tell you the answer and then I'll see if it's less confusing. Oh, struct node, star node. So does this make sense? I have allocated the memory to fit one node struct with malloc, and I have made myself a pointer to a struct node, so the memory address of a struct node, and called it node, because that's really confusingly named. I'll call it A1 because it's an even better name. And so I can go through here and do the same thing for each of these. A1, B1, C1, D1. So now I have a second set of nodes that are exactly the same as these first ones, except they're in a different part of memory. But I've achieved the same goal of, that was drawn terribly. Oh, no I haven't. I've made the nodes, but I haven't actually given them any values or made them point anywhere. So if I wanted to set the data field of A1, how would I do that? It starts with A1, and then it has something, and then it has data equals 10. But what's going to go in here? Remember how with normal structs it's a dot, right? Because struct dot field is the syntax for using a struct. But because it's a pointer to a struct, we would have to take the node and dereference it. And did I do that right? I always get this confused. Take A1, go to the thing that it points to, which is this memory here, and set its data field to be 10. Right, but that's horrible syntax, so we do A1 arrow data equals 10. Those are equivalent. Cool, and so then if we wanted to set its next field, what are we going to do? A1, what are the two characters immediately above this on the line above? Someone said stab, please say arrow instead. Arrow, thank you. A1 arrow, is it Jashank sighing? A1 arrow next equals null. Cool, and so I have made myself a blob of memory of a struct. I've been given a pointer to that struct from malloc. I have set the values of the thing that that pointer is pointing to data being 10 and next being null. Cool, so this code and this code are equivalent, except that this one is inside function memory and this one is inside magical heap sky memory. Let's do this again. That's probably actually going to be a really annoying way to do it. Okay, I'm bored already. I'm not going to make C and D like this. But rather than having to do this over and over again, what could I do instead? Instead of having the same code lots and lots of times, I could instead make a function, yes. So let's make a function to create a node. Some return type, make node, some input. Cool, what is my make node function going to return? It's going to return a pointer to a node because it's going to malloc me some memory and it's going to say, here's the memory for your node. Have this node. Since I want to replace this code that I have here, this annoying code, it's all of these lines, how could I, what input could I take here to avoid having to type all these in the main function? So I can do the malloc thing just fine. I can make myself a struct node called new temp new equals malloc. To avoid that having to set the data in the main function, I could say new arrow data equals 20, but instead of 20 I could take in some value. And then instead of b1 arrow next, I'm making my new one next b null. Cool. So does this make sense? I've made myself a new node inside this function, but because I've used malloc, it will still exist when the function ends. And if I want to give this back to the main function, if I want to say, here's the memory, here's how you get to it, what do I need to return? Someone whispered address. I'm going to pretend you said that loudly and as the right answer. Yes, we need to return how to get to this memory that we've been given, which in this case is the with return in front, which is the memory address of this memory we were given, which is in the variable new. So return new. This function now has allocated some memory, put the value in that we asked it to put in, made its next point to null, and then returned it. And I'm not going to forget my function prototype, because I'm awesome at function prototypes today. Cool. So does this make sense? We've made a function that will malloc some memory, set some value, and then set its next to be null. So I can now replace all of this code. Actually, let's save this as this 3. I can replace all of this code here with struct node star a1 equals make node with the value 10. Cool. Does this make sense? Can you see how this is equivalent? This one here makes me some memory with malloc, or gets some memory, sets the value of the data, sets the next to be null. This function here, make node, takes in this number 10, does all that work for me down here, and then gives me back that memory. So this is all good, this is equivalent, we're sort of happy. Cool, I'm going to pretend we're sort of happy, everything's good. So rather than making myself, like I can then go, struct node star b1 equals make node 20, struct node star c1 equals make node 30, cool, this is great, and I'm having to make all these variables still, so I haven't achieved my goal. Rather than making new node pointers here, what could I do? Let's draw another diagram. If I know that in my node struct, right, I have my value 10 and I have my pointer to some next node. Do I need to make an explicit pointer to b1? Do I need to make in this function, hey b1, make me some memory and call it this variable b1? I don't need to do this, right, because what I can do instead of making a new variable in my function to point to this b1 memory I've gotten, I can make this next field inside a1, point to this new node that I'm given. And so the diagram looks exactly the same. Oh, that points to null for a start. So drawing a diagram, I can say make me a new node, give it the value 20, but make the thing that holds the address of this new node is a1's next field. And so the code for that would look like a1 arrow next equals this thing here. Ugh, try that again. Cool. Does this make sense? Rather than having to make a separate pointer inside my function, I can use this pointer inside this a1 node struct to hold on to the address of where the next node is that I've made. Is this good so far? Are there any questions about this so far? Is that a question? Say that louder. Yes, can I go over it one more time? I can, and I will draw a picture. I'll just hit undo on this picture. Cool. So this line of code, struct node star a1 equals make node. The make node function down here makes me memory for a new node. So malloc goes, here's some memory. Please enjoy this memory. Please put whatever you want in it. So I've been given this blob of memory here. It then sets the value, the data field of that to be the value we've given it. So if we called it with the value 10, it would have the value 10. It sets the next field to be null, which we draw as an arrow pointing to an x. And so this down here, struct node star a1, is given the memory address of this node that we've made. And so now a1, remember I said when we have a pointer, like a struct node star, it's just an arrow. A1 is this arrow here to this node we have here. And so then this one here says A1 arrow next equals make node 20. So we're going to A1, we're taking this point to A1, we're going to the next field of the node struct, and we're making that be equal to make node 20. So make node 20 happens, it makes us a node, puts 20 in, makes it point to null. And then the make node function will return the address of this, and we're saying A1 arrow next equals the address of this memory. And so this is our node A1 in here. Its next field here has the address of this node, so it points to this node. So rather than making a separate variable B1 to hold on to this pointer, we've just said, hey, A1's next field can have this address of this thing that we've just made. Does that make more sense this time? Cool. And so then I can make C1 effectively by going A1 arrow next equals make node 30. And so this here is saying go to the node A1, which is this one here. Go to its next, the thing at its next field, which is this one here. Then make its next field be equal to make node 30. So then it makes me another node, puts 30 in, makes that point to null, and then make node returns the address of this new blob we've been given, and this is saying make the next A1's next field be equal to this address. So that now points to this. Does that make sense still, sort of? If you're thoroughly confused, you can sort of take away the takeaway here is we just add another arrow next on the end, and it just puts a new node on the end. If you don't understand it, you can at least appreciate that this is what the code does. So this one here makes me another node, puts 40 in it, and then makes the next field of 30 point to this node with 40 in it. So was the question, instead of making it point to null every time in here, we could give it the thing to point to? Yes, we could do it that way, but conventionally we make it point to null in here, and then this function just gives us a node, like a new, fresh, pristine node that has just the value in it and doesn't point anywhere. Like, this is kind of conventionally, rather than the syntax has to be like this, if that makes sense. Cool, I am going to comment out all of this code, because all of this code has now been made irrelevant. Cool. And so then let's do our print node over here of A. 1, because it's called A1. So all going to plan, when I say print node A1, it will print me out this value 10 that it contains, and then I'll just delete that code. Down here, it will print me out the value of its data field and then the pointer that it points to, the memory address that it holds for its next field. And so then I should be able to do that on A1 arrow next, which will be printing out the node A1, its next field here, this arrow here, the thing that that points to, which we had called B1 before. But this isn't going to compile. I've preempted the compile error this time. What? Okay. I didn't think that, it's because it's called list3 now. That's why it didn't compile. Cool, so we've gotten all of these error messages that mean nothing to us. Error passing struct node star to parameter of incompatible type struct node dereference with star. And so what this actually means is it's saying you're passing in a node pointer, you're giving me the address of a node, but I expect the node itself. So rather than dereferencing this node when we print it out, let's change this one here to take in a pointer. And the reason for that is because when we pass in the node itself, it will make a copy of it. When you pass a struct in, it'll copy the struct. Whereas if we pass the address of the struct in, it'll copy the address of the struct, but that's only going to be one address big rather than potentially massive for however big the struct itself is. And so now, if I compile it, I didn't fix my function prototype. I was so close. Yes, it compiles. Cool, and so we can see, I'll put these side by side. We've run our list. I'll get rid of that as well, because we're no longer doing that. We've gone struct node star a1 equals make node, so make a node with 10 in it, make a node with 20 in it, that's its next field, and so on and so on. Print out this node a1, which prints out node data and node next. And so that's printed out 10, the node data from this one here, and then this address here, which happens to be the memory address of the one after it that we've just allocated. And then we've said print node a1 arrow next, and that's given us 20 and the address of the one after it. I'm mildly concerned at these values, because that's a stack address, isn't it? Isn't that a stack address? Why are they not heap addresses? It's malloc. Yeah, but why is it should be, what's malloc? What did I do wrong? Okay, I am confused, but apparently this is what it should look like on this system. That is very confusing. Okay, we have printed out some nodes, and those are good. And then we could print out the next one after this with A1 next, next, and next, 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 and this is a horrible way to do it. And then I need another one of those. And all going to plan, this will print out 10, 20, 30, 40, and then nil, because the 40s, the last ones, next points to null. Are you completely sure those are heap addresses? Really? I'm so skeptical, okay. Anyway, computers are strange and they do strange things. Cool, but then this still has the same problem of we've got to type next, 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 and we still can't go whatever size we want it to be, right? So what we can do instead is we can, so this is list 4. If we want to do something lots and lots of times, we could use a loop. Yes, thank you. Someone finally answered my question. And so let's make a loop. Int I equals 0 while something. Let's go while I is less than 10 and just make ourselves 10 nodes. Actually, before we make nodes, let's print out all of the list. So let's write a function to print all of the list. Print list. And so what I want to do is I want to write a function that will, I'll give it this one here. I'll say here's A1, and I want it to print out A1, and then the one after A1, and then the one after the one after A1, and then the one after the one, and so on, right? So I want it to start out at A1. Let me grab a different color. I want it to start out, print out this one, and then print out this one here, which you can do because it knows how to get there from A1, and then print out this one here, and then print out this one here, and then keep going until it's hit the end of the list. Shh. So does that sound fun and exciting? Let's do that. That sounds fun and exciting. So if I want to do something lots of times, I need a loop, as you have told me before, while something. And then I'll do that, okay. So if I want to keep track of the current one that I'm up to, so rather than having to chain, A1, arrow next, arrow next, arrow next, if I want to sort of be able to go whatever node that I'm looking at, like look at this node here, and then go to its next field. And so sort of look at this one here, and then go to its next field and look at this one here, and so on. I can do a thing. In order to do this diagram that I've drawn, right, I need to sort of have a blue arrow that starts at this one, and then I want to have the blue arrow point at this one, so that each time I can sort of have my arrow going, here's the current node that you care about, let's print out this node. So I will do that by saying struct node star current. And so this line of code, struct node star something, has made me an arrow. Like, this is a really important distinction to get. When I say struct node star something, all I have is an arrow. I don't have a node. I haven't made an actual node, an actual thing of memory. I just have an arrow that will point to a node. I hope you understand this. This is an important part to understand. And so while something, I don't really care, let's printf current arrow data equals %d current arrow data. And so this is the same printf from here before, right? We have some node pointer. We go to the node at that node pointer, get its data field, and print that out as a number. And so this one here, assuming that we already have a pointer, like a node star, an arrow that points to some node called current, I can then go to the data field of the node that current is pointing to and print that out. So if I want to start out by printing the first thing in the list, where do I want my arrow to point to? A blue arrow I draw here. If I want to print out the first thing in the list, where should it point to? I'll give you a clue. The answer is the first thing in the list. If I want to start out by going to the first thing on the list, I want to go to the first thing in the list. Are you all just thoroughly confused, or? Okay, well, let's keep going. We're almost there. So I make myself this blue arrow here. It's called current, C-U-R-R. Conventionally, if we're talking about the current thing we're pointing to, we just say C-U-R-R because that's much shorter to type and we're lazy. So if I say struct node star current equals node. So this line of code here is saying, make me an arrow, make me a thing that will hold the address of a struct node, and make it be equal to node. And in this case, node itself is also the address of a node. And so this is saying, here's my A1 pointer. I'll actually call it node here. So node is an arrow pointing to this blob of memory here. When I say current equals node, I'm saying make this also point to the same place as node. So a new arrow that points to the same place as that one. And so then if I get rid of my while loop and just print this one out, what this should do is this should print out the data that was in the first node I gave it, so in A1. So I'll put that here. Oh, print list A1. I will comment that out. Cool. So does this make sense so far? I've got a struct node star A1 equals make node, so it makes me a node, puts 10 in it, gives me A1 as an arrow to it, makes some more nodes, joins them together, calls the print list function, which takes in A1, which is the address of the node, this 10 here. Print list will then make a new pointer, a new struct node pointer, which is just a new arrow that points to the same thing as node, and that will print out the data field of that node that it points to. Hopefully this is all good thus far. List 4. Oh man. Did I forget to do a function prototype? Yeah. I got it right the first couple of times. Yeah, clear. TCC. Yay, it compiled. So now if I run list, I'm expecting that this will print out current arrow data equals 10, because it'll just look at this node A1 that contains 10. And indeed it has printed that out. So what this code is doing, it's got a pointer to this first node here, to the node, the first one on the list with the 10, and then it's printed it out. Okay, cool, we've just printed out one thing, that's fine, we could do that already. What do I do if I want to make my blue arrow here, my current pointer, if I want to make that point to the next node in the list, how do I do that? I'll give you a slightly easier question. Looking at my node that I have here, right, this one with the 10 in it, how do I get to the node that it points to? Which thing inside that node contains the address of the next one? Yes, next, right? So this next field here, this, the second part of the node that is a pointer to the next node is a pointer to the next node. And so we can follow that pointer along, and from that pointer, get to this next node here. And so current arrow next is the next field of the thing that current is pointing to. So when current is pointing to the 10, current arrow next is this arrow here that points to 20. So if I said current equals current arrow next, what I'm saying is current points to this node for a start, this 10, go to the thing that its next field points to, and current is now going to point to that. So I'm changing the value of my blue arrow to, instead of having the memory address of the 10, have the memory address that was stored inside its next field, which is the memory address of the 20. Does that make sense? Who is thoroughly confused? Who is awake for a start? Okay, that's like maybe 20%. Who is awake but didn't raise their hand because they don't like raising their hand in lectures? Who didn't raise their hand that time either because, yep. So that's the problem, right? But what I'm going to do, I'm going to copy this printf. So printf current data is this. I'm then going to change current. Current is my arrow. Current points to some node. I'm going to make that point to the next node and then print out the data again. So this should print out 10 and then 20. It will print out the contents of the first node with the 10, and then move current to the next node and then print out the 20. If I got this right. It compiles. It runs. And so we've printed out current arrow data is 10, and then current arrow data is 20. Very good. And so how could we generalize this? How could we put this in a loop? If I just do this, right? I'll just go while forever. While 1. So 1 is like true, and so while 1 just means go forever. So let's say while forever, print out the current data, and then make current point to the next one. And so that means my blue arrow here is going to start out pointing to the 10. It will then change to point to the 20, and then it'll change to point to the 30, and so on. So what do you think will happen here? Before the part where something goes wrong, what will this print out? 10, 20, 30, 40. Yes, so I hope. Let's run it and see. Excellent. We got 10, 20, 30, 40, and then runtime error member access with a null pointer of type struct node. Thank you, GCC. But let's live dangerously. Let's compile it with GCC and see what happens. So DCC, I've said before, it has these things in where it'll tell you if you're doing something bad and it'll stop you. Compilers like GCC do not. And so if I compile it with GCC, it's printed out 10, 20, 30, 40 like I wanted, and then it said segmentation fault. Has anybody seen a segmentation fault before? A couple of you. You will get very used to seeing these if you code in C for much longer. They'll become your friend. What a segmentation fault means is it means that you have tried to access a segment of memory that you're not allowed to access. And in this case, a null pointer points nowhere, and if you try to access nowhere, you can't. So what can I make my loop condition be if I want my loop to stop when I've hit the end? Let's walk through this in the picture. Let's improve my picture slightly. So remember, with my list, 10, the node with 10 in it points to the node with 20 in it, points to the node with 30 in it, points to the node with 40 in it, and then its next field is null. Shh. We are very nearly finished. So if I'm going to keep on updating current to point to the next field, so current will start out pointing to this one, and then it'll point to this one, and then it'll point to this one, and then it'll point to this one. And then after it's finished 40, it'll then point to 40's next field, which is null. So how do I know if I've hit the end? Yeah, if I've hit the null on the end. So when I go through this, current is the node, current equals current next. That's going to point to the next one, the next one, the next one, and so on. Current becomes the address of the thing that the next one is pointing to, like the next address of the thing. And so when this hits the end, current will be null. Current will have hit this x here. Current will have gone to the null pointer. And so I can say while current does not equal null, print out the data, and then current is current next. And so what this will do, current will start out pointing to the first one, it'll point to the next one, the next one, the next one, and so on. And then when it goes from 40 to that null pointer, it will stop, hopefully. Let's compile it and see. ./list. Woohoo, it's printed out 10, 20, 30, 40, and then it has stopped. What a great place to finish. So I hope that you've learned something. If you're confused, that's fine. Ask me now, post on the forum, we'll answer things on the forum. Otherwise, do the weekly quiz, start your assignment. Have a good week.